Florence, Italy. The year is 1495. Leonardo da Vinci stands in his workshop, candlelight flickering across dozens of sketches pinned to the walls. Gears. Everywhere, gears. Spur gears with straight teeth. Bevel gears that change the angle of rotation. Worm gears that can multiply force by incredible ratios. His hands are stained with ink and chalk dust as he draws yet another variation, turning the paper to examine it from different angles. He's frustrated. The gears of his time, the ones he sees in mills and clocks, they work technically. They turn. They transfer motion. But they're crude. The teeth are often uneven, cut by hand with files and chisels. They wear down quickly. They catch and skip under heavy loads. They make noise, grinding, clicking sounds that betray their inefficiency. Leonardo knows there's something better, something more elegant. He can see it in his mind. Gears that mesh so perfectly, they're almost silent. Gears with teeth shaped like precise mathematical curves. Gears that could do things no one has even imagined yet. But here's what makes Leonardo's obsession so fascinating. He's not the first person to think about gears, not even close. By 1495, gears have already been around for over 1,500 years. Ancient civilizations built machines with gears that would astonish even Leonardo if he could see them. And yet somehow, that knowledge was lost, scattered, waiting to be rediscovered. And after Leonardo, his ideas would sleep in notebooks for centuries before anyone could actually build the machines he imagined. The story of the gear wheel isn't the story of one inventor in one moment. It's the story of human ingenuity building, disappearing, and rebuilding across thousands of years. And Leonardo da Vinci sits right in the middle of that story, frustrated by the past, dreaming of the future, and never quite able to bridge the gap between the two. So let's start where Leonardo started. Looking backward, what did the ancients know about gears that Leonardo's world had forgotten? And how did we get from those first toothed wheels to the Renaissance workshop where Leonardo sketched his dreams? To understand what Leonardo inherited, we need to go back to the very beginning. Around 3500 BCE in ancient Mesopotamia, someone invented the wheel. But it wasn't for transportation. It was a potter's wheel, a flat disc that spun clay so potters could shape vessels with unprecedented speed and uniformity. This was revolutionary, but it was just the beginning. The problem with wheels is that they only do one thing. They rotate around a single axis in a single direction. If you want to change what a wheel does, change its speed, its direction, its purpose, you need something more. The first step toward gears probably came from something called a windlass, a cylinder that could lift heavy loads by winding rope around it. Ancient builders in Egypt, in Mesopotamia, discovered that if you inserted wooden pegs around the edge of the windlass wheel, you could push against them for leverage. Even better, you could use a pawle, a catch, to prevent the wheel from spinning backward and dropping your load. These pegs weren't gears yet, but they were the conceptual ancestor, a wheel with deliberate interruptions that could interact with other objects in controlled ways. The real breakthrough came sometime around the 3rd century BCE in the Greek world. We know this because of an impossible artifact. In 1901, sponge divers found a shipwreck off the Greek island of Antikythera. Among the recovered artifacts was a corroded lump of bronze and wood. For decades, it sat in a museum, dismissed as unremarkable. Then, in 1951, a scientist named Derek de Sola Price began examining it with X-rays. What he found shouldn't have existed. The Antikythera mechanism, as it came to be known, contained at least 30 bronze gears arranged in a complex mechanism. It was an astronomical calculator built around 100 BCE, designed to predict the positions of the Sun, Moon, and planets. It had differential gears, the same principle used in modern car transmissions. It had epicyclic gearing, where gears rotate around other gears. The level of sophistication wouldn't be matched for over 1,000 years. Someone in the ancient world, possibly working in the tradition of Archimedes, the legendary Greek mathematician, understood not just how to make gears, but how to make them work together in systems. They understood gear ratios, that a small gear driving a large gear slows rotation, but increases torque, while a large gear driving a small one does the opposite. This wasn't just craftsmanship. This was mathematics made physical. The Romans inherited this knowledge. The architect Vitruvius, writing around 15 BCE, describes watermills with geared mechanisms that convert the horizontal rotation of a water wheel into the vertical rotation of millstones. These mills spread throughout the Roman Empire, grinding grain on an industrial scale. But then something tragic happened. The knowledge faded. When the Roman Empire collapsed in the West, the infrastructure that supported complex manufacturing collapsed with it. The great centers of learning fragmented. For several centuries, European technology actually regressed. The sophisticated gear mechanisms of the ancient world became legends, then rumors, then forgotten entirely. This is what Leonardo inherited, a world that had lost touch with its own mechanical past. But knowledge has a way of surviving, even when empires don't. While Europe struggled through its dark ages, other civilizations were advancing the art of gearing in spectacular ways. In 1092 CE, in the Chinese city of Kaifeng, a Buddhist monk and engineer named Su Song completed something extraordinary, an astronomical clock tower over 30 feet tall. The cosmic engine, as it was called, used water power and a complex array of gears to drive multiple functions simultaneously. It displayed the time. It showed the positions of celestial bodies. Mechanical mannequins emerged to ring bells and strike gongs. At the top, an armillary sphere rotated to track the stars. Most importantly, Su Song's machine used an escapement mechanism, a device that converted continuous water wheel rotation into discrete, measured movements. This is the principle that makes mechanical clocks possible, and Su Song built it 3 centuries before it appeared in Europe. When the cosmic engine was destroyed in 1127, Su Song's detailed treatise survived, preserving the knowledge. But that knowledge stayed in China. Leonardo, working in Italy almost 400 years later, never heard of it. Meanwhile, in the Islamic world, engineers were pushing gear technology in different directions. In 11th century Cairo, Al-Jazari created elaborate water clocks and automata with complex gearing. In Baghdad, scholars preserved Greek texts on mechanics and expanded upon them. This is the hidden history that Leonardo couldn't access. Across the world, across the centuries, brilliant minds had been solving the same problems, discovering the same principles, building geared machines of stunning sophistication. By the time Leonardo was born in 1452, European clockmakers had rediscovered some of these principles independently. Mechanical clocks, driven by falling weights and regulated by escapements, had been appearing in church towers and town squares since around 1280. These clocks trained a new generation of craftsmen in the art of gear making, but the gears were still crude, by ancient standards, still inefficient, still limited. This was Leonardo's inheritance, a glimmer of what gears could do, surrounded by centuries of lost knowledge and unrealized potential. So what drove Leonardo to fill notebook after notebook with gear designs? What did he see that others missed? Part of it was pure intellectual curiosity. Leonardo was fascinated by how things worked, not just mechanically, but fundamentally. He dissected corpses to understand human anatomy. He studied the flow of water to understand fluid dynamics. Gears, for him, were another mystery to unravel. How could simple geometry create such profound effects? But there was also frustration. Leonardo was a court engineer, employed by wealthy patrons to design practical machines, weapons, fortifications, irrigation systems, and everywhere he looked, he saw machines limited by the gears of his time. Lifting heavy stones for construction, the gears in the cranes ground and skipped under load. Milling grain, the gears wore down quickly, requiring constant maintenance. Maintaining accurate time, even the best clocks gained or lost minutes each day because their gears didn't mesh smoothly. Leonardo understood that gears were a universal tool, applicable to any problem involving motion and force, but they needed to be better. His notebooks reveal a systematic investigation. He drew hundreds of gear designs, exploring every variation he could imagine. Spur gears, the simplest kind, with teeth parallel to the axis of rotation. Bevel gears, with teeth on cone-shaped surfaces, allowing rotation to change direction. Worm gears, where a screw-like gear meshes with a regular gear, creating massive speed reduction ratios. Lantern gears, with cylindrical pegs instead of cut teeth, easier to manufacture, but less efficient. He designed a spring-powered cart that used gears to transfer stored energy to wheels, essentially a clockwork car. He designed an odometer that used gears to count wheel rotations and convert them to distance. He designed machines that could raise water, move earth, spin thread, all driven by cleverly arranged gear trains. But Leonardo's most important contribution wasn't any specific machine. It was his investigation of gear-tooth geometry. The gears of his era had simple, straight-sided teeth. They worked, but they created jerky motion. The teeth would catch, release, catch again, creating vibration and wear. Leonardo realized that the shape of the teeth was critical. He began experimenting with curved tooth profiles. If the teeth were shaped correctly, he reasoned, they could maintain constant contact as they meshed, creating smooth, continuous motion. He filled pages with geometric constructions, trying to find the ideal curve. He didn't fully solve the problem. The mathematics were beyond what was possible in his time, but his intuition was correct. The ideal gear tooth is shaped like an involute curve, and Leonardo's drawings show him moving in that direction. He also understood something else crucial. Precision matters. A gear is only as good as its manufacturing. If the teeth are uneven, if the spacing is inconsistent, if the material is weak, the gear will fail. Leonardo sketched ideas for gear-cutting machines, for measurement tools, for quality control methods. But here's the tragedy. Almost none of Leonardo's gear designs were built in his lifetime. Some were too ambitious for the technology of his era. His continuously variable transmission, for example, required manufacturing precision that wouldn't exist for centuries. Some were too expensive. His patrons wanted practical weapons and fortifications, not experimental mechanisms. And some were simply ahead of their time, ideas waiting for the right moment. When Leonardo died in 1519, his notebooks were scattered among his students and heirs. Some were lost, others sat in private collections, unseen for centuries. His gear designs, his systematic investigations, his geometric insights, his vision of what gears could become, they didn't directly influence the development of gear technology. And yet Leonardo's obsession reflected something real. The Renaissance was a time when Europe was beginning to rediscover mechanical sophistication. The knowledge that had been lost with Rome, that had evolved in China and the Islamic world, was being rebuilt from scratch. Leonardo stood at the cusp of that rebuilding. He could see where gears needed to go, even if he couldn't quite get them there himself. What happened after Leonardo? How did we get from his sketches to the precision gears of today? The answer is slowly, then all at once. For about 150 years after Leonardo's death, gear technology advanced incrementally. Clockmakers got better at their craft. The teeth became more uniform. The materials improved. But there was no revolutionary breakthrough. The real change came when gears became a scientific problem, not just a craft problem. In the 17th century, astronomy drove the first major advances. Astronomers like Ola Römer, who calculated the speed of light in 1674, needed extraordinarily accurate clocks to time celestial observations. Those clocks needed extraordinarily precise gears. This created a feedback loop. Better gears enabled better instruments, which enabled better science, which demanded even better gears. The mathematics of gear tooth geometry became a serious field of study. In 1765, a Swiss mathematician named Leonhard Euler published theoretical work proving what Leonardo had intuited. The ideal tooth shape is a specific curve, an involute, that maintains constant contact and smooth motion. Euler didn't just describe this curve, he provided the mathematics to calculate it exactly. For the first time, gear designers could move beyond trial and error. They could design optimal gears on paper, then manufacture them to specification. But knowing the ideal shape and actually cutting it were two different problems. That's where John Harrison comes in. In 1714, the British government offered a massive reward, the Longitude Prize, for a method of determining a ship's longitude at sea. Harrison, a self-taught clockmaker, believed the solution was a clock accurate enough to work on a rolling ship. If you knew the exact time at your home port and compared it to local noon, you could calculate your longitude. Harrison spent over 40 years perfecting marine chronometers. His solutions involved ingenious gear mechanisms that compensated for temperature changes, that maintained constant power delivery as the mainspring unwound, that resisted the effects of motion and humidity. His H4 chronometer, completed in 1759, was accurate to within 1 second per day, extraordinary for the time. When it finally won the prize in 1773, after years of bureaucratic resistance, it proved something crucial. With sufficient precision in gear manufacturing, mechanisms could be made reliable enough to stake lives upon. Harrison's work established new standards for what gears could be, but making gears to those standards remained expensive and time-consuming. Each gear was still hand-cut by skilled craftsmen. Then came the Industrial Revolution, and everything changed. The steam engine, perfected by James Watt in the 1770s and 1780s, created a new problem: abundant rotary power that needed to be distributed, controlled, and transformed. Gears became essential industrial components, not luxury items for clocks and instruments. In textile mills, gear trains transferred power from central steam engines to hundreds of looms and spinning machines. In coal mines, gears connected steam engines to pumping mechanisms. In locomotives, gears connected pistons to drive wheels. The demand for gears exploded, and with it came the innovation that would finally make Leonardo's dreams possible: the gear-cutting machine. In 1835, British engineers developed machines that could cut gears using, appropriately enough, gears. This is worth pausing on. Once you could make gear-cutting machines, each generation of machines could make better machines. Precision begat precision. By the mid-19th century, gears were being mass-produced for the first time. They were still expensive, still requiring significant skill to manufacture. But they were no longer one-off artisan creations. They were industrial products. This democratization of gear technology accelerated other innovations. When you could reliably obtain gears of various sizes, you could design more ambitious machines: the sewing machine, the bicycle, the typewriter, the phonograph. All depended on gears to function. In 1885, Carl Benz built what's often considered the first true automobile. At its heart was a gear-based transmission. The automobile industry would become one of the largest consumers of gears in history, driving continuous improvements in design, materials, and manufacturing. By 1900, the world Leonardo had dreamed of, a world where gears were precise, reliable, and ubiquitous, had finally arrived. Not because of his notebooks, which were only beginning to be widely studied, but because the same logic he'd followed had been followed by countless engineers, each building on the work of those before. The 20th century took gears to places Leonardo couldn't have imagined. Aviation demanded lightweight, high-strength gears that could operate under enormous stress. This drove innovations in materials: high-grade steel alloys, heat treatments that hardened surfaces while keeping cores flexible, eventually exotic metals and composites. Automobiles demanded gears that could last hundreds of thousands of miles with minimal maintenance. This led to precision manufacturing techniques capable of producing gears with tolerances measured in microns, millionths of a meter. That's a level of precision Leonardo couldn't even conceptualize. But perhaps the most unexpected application came with computers. Charles Babbage's analytical engine, designed in the 1830s but never completed in his lifetime, would have used thousands of gears to perform calculations. Each gear represented a digit. Gear ratios represented arithmetic operations. It was Leonardo's insight taken to its logical extreme. Gears as mathematics made physical. When electronic computers emerged in the 1940s and 50s, they still used gears extensively in peripherals: printers, disk drives, tape readers. Even today, hard drives use precision gear mechanisms, and 3D printers rely on gear-driven motion systems. The mathematical understanding of gears also reached new heights. Engineers developed computer simulations that could predict exactly how gears would perform under load, how they would wear over time, how they would behave at different temperatures. Leonardo's intuitive geometric explorations became rigorous numerical analyses. Modern manufacturing has made things possible that would seem like magic to Leonardo. Computer numerical control, CNC, machines can cut gears with extraordinary precision, maintaining tolerances that ensure whisper-quiet operation. 3D printing allows for gear geometries that would be impossible to manufacture by traditional methods. Internal gears, planetary gear sets, even gears that morph their shape under load. Speaking of planetary gears, these are perhaps the purest expression of Leonardo's vision. In a planetary gear set, Multiple gears rotate around a central sun gear, held in a ring gear. They provide enormous gear ratios in compact spaces. They're in automatic transmissions, wind turbines, electric car motors. They're elegant, efficient, and would have delighted Leonardo. And yet for all this sophistication, the fundamental principle remains exactly what it was when the first ancient Greek craftsman cut teeth into a bronze wheel. Circular motion transferred through the mesh of teeth. Geometry transformed into force and speed. So what's Leonardo's place in this story? He didn't invent gears. They were ancient when he was born. He didn't build the machines he designed. Most remained as drawings. He didn't solve the mathematical problems he identified. That would take another 2 centuries. And yet, his obsession tells us something important about how innovation actually works. Leonardo's notebooks weren't published widely until the 19th century, long after the gear technology he imagined had been developed independently by others. His direct influence on gear development was minimal, but his notebooks reveal that he was asking the right questions. The problems he identified, tooth shape, precision manufacturing, the limitation of materials, those were exactly the problems that subsequent generations of engineers would solve. He saw the path forward even if he couldn't walk it himself. Leonardo's real legacy is the mindset he represented. The idea that machines are worthy of systematic study, that practical problems can be solved through geometric insight, that there's always a better way if you're willing to think deeply enough about the fundamentals. When engineers in the 18th and 19th centuries began to scientifically study gears, they were following Leonardo's approach, even if they'd never seen his notebooks. When Euler solved the tooth geometry problem mathematically, he was answering questions Leonardo had asked. This is how innovation actually accumulates. Not through lone geniuses working in isolation, but through generations of people asking similar questions, each moving the needle a little further, each constrained by their time's technology, but pushing toward the same goal. Leonardo stands at the center of the gear wheel's story, not because he changed its trajectory, but because he exemplified it. He looked backward at what the ancients had achieved and forward to what might be possible, all while struggling with the limitations of his present. That's the position every engineer is in. We inherit solutions from the past. We imagine futures we can't quite reach, and we work with today's tools to move a little closer. Let's pull back and see the whole story now, from beginning to end. Around 3500 BCE, someone in Mesopotamia invented the wheel. Simple, revolutionary, but limited. By 100 BCE, Greek craftsmen were building mechanisms like the Antikythera device, sophisticated gear systems that computed astronomical events. The knowledge existed. The capability was there. Then, for complicated reasons involving empire collapse and knowledge fragmentation, much of that sophistication was lost to Europe. It survived and advanced in China and the Islamic world, but those advances didn't flow back. By 1280 CE, European clockmakers were independently rediscovering gear mechanisms, rebuilding what had been lost. Leonardo, in 1495, inherited this partial rediscovery. He could see that gears should be better, more precise, more capable, but he couldn't quite make them so with the tools of his time. After Leonardo, the path forward required 2 things: mathematical insight, provided by Euler and others in the 1700s, and industrial manufacturing, enabled by the Industrial Revolution in the 1800s. By 1900, gears had become ubiquitous, precise, and reliable, everything Leonardo had imagined. And in the 20th and 21st centuries, gears became both more sophisticated, computer-designed, manufactured to micron tolerances, and more fundamental, embedded in everything from watches to wind turbines. The story of the gear wheel is the story of human problem-solving across time. It's not a straight line. Knowledge gets lost, then rediscovered. Problems get solved multiple times in multiple places by people who never hear of each other. Innovation happens in fits and starts, constrained by available technology, enabled by new insights. And individuals like Leonardo, they're not lone inventors. They're nodes in a network, connecting past to future, asking questions that point towards solutions they won't live to see. The next time you shift gears in a car, or hear a clock tick, or watch a mechanical device do its work, think about the thousands of years of human ingenuity embedded in those meshing teeth. Think about the anonymous Greek craftsman who first cut gears into bronze. Think about Su Song in China, building his cosmic engine. Think about Leonardo in his workshop, frustrated by crude gears but sketching perfect ones. Think about Euler solving the mathematics, Harrison perfecting the craft, and countless industrial engineers making it all cheap enough to put in every machine. The gear wheel isn't just a mechanical component. It's proof that human knowledge can accumulate across time, that each generation can build on the last, that problems can persist for centuries before someone develops the tools to solve them. Leonardo saw where gears needed to go. It took humanity another 400 years to get there. But we got there because people kept asking his questions, kept pushing toward his vision, kept believing that circular motion and geometric teeth could do more, be better, reach further. That's the real invention. Not the first gear, but the persistent refinement across millennia. The gear wheel, as we know it today, was invented by everyone who ever tried to make it better. And somewhere, in some workshop, someone is still trying to make it better still. That's the invention of the gear wheel.